Diagonalization. A square matrix A is diagonalizable if A is similar to a diagonal matrix. That is, that A is equal to P times D P inverse for some invertible matrix P and some diagonal matrix D. So let's consider a 2 by 2 matrix. Let's consider a 2 by 2 matrix. And let this matrix has lambda 1 and lambda 2 eigenvalues with corresponding eigenvectors v1 and v2 respectively. What that means that A times v1 is equal to lambda 1 v1 and A times v2 is equal to lambda 2 v2. So now we consider A times the matrix that the columns are the eigenvectors v1 and v2. By the matrix property, we can multiply this A inside, so I still have the matrix. And A times V1 is nothing else but lambda 1 V1, right? So we would substitute this for A V1 and the other one for A V2. That's what I'm getting right here. Now, if I factor or rearrange this, I'm gonna get this form. If you multiply row times column, we're gonna get what we had before. So that operation is equivalent. So if we look at this, point, so look at the beginning. Here we go. So look at the beginning. We have A times V1 is equal to A V1 V2 lambda 1 lambda 2. So the V1 matrix, so this matrix V1 we will call matrix P. V1 matrix is gonna call it the matrix P. So what did I get is A times P is equal to P times D. Now from the right side I would multiply that equation by P inverse, and P inverse is identity, so I'm left with the A equals to P times D P inverse, which is nothing else but the diagonalization of that matrix. So that's the diagonalization theorem, is that let n by n matrix be A is diagonalizable if and only if A has n linearly independent eigenvectors, because the matrix P is composed from eigenvectors. In that case, A is equal to PD P inverse. D, we put eigenvalues on the main diagonal. It's a diagonal matrix, so that means zeros are everywhere else. And the P is corresponding eigenvectors. So this is my lambda 1, corresponding eigenvector is V1. So as long as we have enough of those eigenvectors, in that case, the matrix will always be diagonalizable. So let's look at the example. Diagonalize each matrix if possible. So for first example, the matrix is triangular. The eigenvalues are the elements on the main diagonal. So my eigenvalues are 1 and minus 1. Now we need to find corresponding eigenvectors. So if I have 1, I'm solving the equation AX. I'm solving the equation AX A minus lambda identity X is equal to 0. We're solving this for x, for a non-zero vector x. So in other words, I'm subtracting 1 from the main diagonal. So if I subtract 1 minus 1, I'm getting 0, and minus 1 minus minus 1 minus 1, I'm getting minus 2. It should be minus 2 right here. Minus 2. So then if I reduce this form, I'm still gonna get exactly the same. So I only have little error right here. It should be -2 on this one. But for after reducing, divide by 6, you're gonna get 1, and multiply times 3 and add it, we're gonna still get 0. So the eigenvector is indeed 1 and 0 here. Then for lambda equal to -1, I would subtract minus -1, so I'm going to add 1 to the main diagonal. So the 1 plus 1 is 2, -1 plus 1 is 0. So in that case, I'm getting this. When I solve this equation, I'm getting eigenvector right here. So I have 2 eigenvalues and 2 eigenvectors. So my P matrix is equal to the eigenvectors. I put them as an eigenvectors. And on the main diagonal, I'm putting eigenvalues. So the diagonalization is P, D, P inverse, where P is the matrix given here and D is the matrix given there. Now for the second matrix P, first we need to find eigenvalues. This matrix is not triangular, so we need to find eigenvalues by solving this, by solving the equation determinant B minus lambda identity I equal to 0. So subtract the lambda on the main diagonal, 3 minus lambda, 5 minus lambda, and then this is the determinant. So we're solving the determinant, cross multiply lambda minus 3 minus lambda, 5 minus lambda, minus cross multiply the other diagonal, right? So plus 1, and solve this equation, reduce it, perform, and we're getting that the eigenvalue is 4. So next we need to find the eigenvectors. So to find eigenvectors, we solve the equation A minus lambda identity x equal times x equal to 0, so -4. So we subtract 4 on the main diagonal from the matrix and we solve the equation. So if I subtract 4 on the main diagonal, I'm getting -1 and 1. And it's right here. Then we perform the row operation, solve the system, and I only have one free variable, so I have only one eigenvector. So the diagonalization would be of this form, where D, I would put the eigenvalues, but because I only have one eigenvector, I don't have anything else. And in that case, we can conclude that the matrix is not diagonalizable. I don't have enough eigenvectors. Number 3, the same way, we're finding first eigenvalues by solving this equation. So subtract lambda, this is the determinant we need to find. Add the rows, try to reduce as much as possible. Then we would expand. Then we would expand by the first, expand by the last row. So I would have 0 times cofactor, then we have -3 times the -1 position of third row second column times the determinant by deleting the third row and second column, so whatever is left. And then we have plus -3 minus lambda, -1 to the power position is 3, third row and third column, and then whatever is left, that's my determinant. Now pay attention how you solve this one, because you try to keep factoring as much as possible. If you multiply everything out, you're gonna get polynomial of degree 3, and then it's pretty hard to solve it. So in that case, as you notice right here, we try to factor 3 minus lambda out right away. And then we keep solving, performing those determinant, and then the other determinant is right here. So if you reduce and perform, then you have square and square quadratic polynomial. It's easy to factor than the polynomial of degree 3. So it is very beneficial to keep factoring as much as possible as we keep going. So once we have all the eigenvalue, once we find all the eigenvalue, next step is to find the eigenvectors. So first we're gonna find the eigenvector corresponding to 3. So it is more beneficial to keep starting finding eigenvectors for the eigenvalue that has multiplicity 2 or 3, because eigenvector, I can have 2 eigenvectors or I can have 1 eigenvector. If I have only one, then I would not have enough for the diagonalization. So let's find the eigenvector corresponding to lambda equal to 3. So we're solving the equation as before. Subtract 3 on the main diagonal to get this matrix. Reduce, perform row operation, basically solve. We have 3 variables, and if I solve this, I'm getting this one is cutted. I'm getting those 2 eigenvectors. Right here, this is the one, this is the other one. So we have 2 eigenvectors for the eigenvalue with multiplicity 2. In that case, we will have enough eigenvectors for diagonalization. So then we perform the same for lambda equal to 1, subtract 1 on the main diagonal, get the matrix, reduce, perform row operation, basically solve the system, and find the eigenvector. Then the diagonalization is nothing else but C is equal P, D, P inverse. D is the diagonal matrix with the diagonal elements on the main diagonal eigenvalues. And then corresponding eigenvectors are those ones that we found. Just pay attention, if you first put 3, then you need to have the corresponding eigenvectors to the 3, and then this one to the corresponding to 1. So couple properties, we have the dimension of an eigenspace for the given eigenvalue is always less than or equal to the multiplicity of the eigenvalue. So eigenspace means how many eigenvectors we can get. So for this eigenvalue we had 2. For this eigenvalue we have 2. So because the eigenvalue was of multiplicity 2. If we look right here, the multiplicity is 2. So the eigenspace, how many vectors I have from right here corresponding to this eigenvalue, is at most 2. I can have 1 or 2. Always 1, because that's the definition of eigenvalue. So the dimension is less than or equal to the eigenvalue that we have. And then we have matrix with n distinct eigenvalues is always diagonalizable, and that also should make sense, because if you have distinct eigenvalues, each eigenvalue needs to have one eigenvector. That's by definition. So if you have distinct, then you're gonna have different eigenvectors. So you're always gonna have an eigenvectors, and they turns out to be linearly independent. So then we can always diagonalize the matrix. Now we have example, and in that case, for a 4x4 matrix with 2 eigenvalues, one eigenspace is 2-dimensional. What are the possible dimensions of the other eigenspace? Can A be diagonalizable? Explain. So we have 2 eigenvalues, but the matrix is 4x4. So that means they have multiplicities, right? They said one eigenspace by eigenspace is 2-dimensional. So that means it has multiplicity or 2. 2-dimensional, I have 2 vectors. I have 2 eigenvectors. But the multiplicity could be 3, right? Because we can have two eigenvectors. If the multiplicity is 3, we can have 3 eigenvectors, 2 eigenvectors, or 1 eigenvector, always less. So for lambda, we have v1, v2. So lambda 1 has multiplicity or 2 or 3. if lambda has multiplicity of 2, we have 2 eigenvectors, and then the other one needs to has multiplicity of 2. But in that case, the other eigenvalues can have multiplicity of 1, can have 1 vector or 2 vectors. So if lambda has 2 vectors with the matrix of 2 vectors, then the matrix is diagonalizable because I would have enough eigenvectors. If the other eigenvalue has 1 vector, then the matrix would not be diagonalizable. Now, if my original lambda 1 has multiplicity 3, but has only 2 eigenvectors, because that's given that the eigenspace is 2, then lambda 2 has multiplicity only 1, because the total multiplicity must be no more than the size of the matrix, and only 1 eigenvector. In that case, the matrix is not diagonalizable, because my P matrix would be this, would have 1, 2 from the 2 eigenvectors that I have right here, and then from the 1 I'm gonna get the another one, but here I don't have the eigenvector. I don't have the other eigenvector. So that means it's not diagonalizable in that case. And diagonalization of a matrix is used to compute powers. That is, if A is diagonalizable, then the matrix is such that there are matrices P and D such that A is equal to this. And if I compute powers, I would take to the power P. That means I would repeat, and then the P and P inverse are identity. So all of them between gonna be identity. So what I'm gonna be left is P times D times D times D times D times D. And at the end, I'm gonna be left with P inverse. So that means that D is to the power K, and that's what I have here.